The James Webb Space Telescope was designed to see the earliest galaxies in the universe, objects so far away that their light has been traveling for more than 13 billion years. What nobody fully anticipated was what it would find when it looked that far back. Not just faint smudges of ancient light, but organized, structured, fully formed galaxies existing in an era when the physics of galaxy formation says they had no business being there. That discovery alone would have been significant, but Webb did not stop there. In the same period that it was rewriting the early history of the universe, it was also pointing at a planet 124 light-years away and detecting a gas in its atmosphere that on Earth is produced almost exclusively by living organisms. And it turned its infrared instruments toward Neptune, a planet we have been studying for decades, and found things in its atmosphere and magnetic field that nobody expected. These are not isolated results. They are part of a pattern that has been building since Webb began operating. Each new observation has not simply added detail to what we already knew. It has uncovered places where the existing models of the universe are incomplete or, in some cases, fundamentally wrong. To understand why these discoveries carry the weight they do, it helps to start with what the standard picture of the universe looked like before Webb arrived. The Big Bang occurred approximately 13.8 billion years ago. In the moments and centuries immediately following, the universe was an extraordinarily hot, dense plasma. Temperatures were too high for atoms to remain stable. Protons and electrons existed separately, colliding constantly. Light could not travel freely, it was continuously absorbed and re-emitted in a fog of charged particles. After about 380,000 years, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, called recombination, allowed light to travel for the first time, and the universe became transparent. That ancient light is still detectable today as the cosmic microwave background, a faint glow of microwave radiation that fills the entire sky uniformly, a thermal remnant from that moment of first transparency. After recombination, the universe entered what cosmologists call the cosmic dark ages. There were no stars, there were no galaxies, there was only hydrogen gas, slowly cooling, very gradually being pulled by gravity into denser concentrations. This process took time. The gas had to cool enough to collapse. The collapsed regions had to become dense enough to ignite nuclear fusion. The resulting stars, the first generation, called population 3 stars, had to live, die, and enrich the surrounding gas with heavier elements before the next generation could form. The first stars are estimated to have appeared roughly 100 to 200 million years after the Big Bang. They were made almost entirely of hydrogen and helium because those were the only elements in abundance at the time. They were probably very massive, perhaps hundreds of times the mass of the Sun, and they burned through their fuel quickly, living for only a few million years before exploding or collapsing. Galaxies came later, or at least that was the model. For galaxies to form, individual stars needed to cluster together under gravity. Gas needed to organize into rotating disks. Dark matter halos needed to provide the scaffolding for baryonic matter to accumulate around. This was understood to be a gradual process, unfolding over hundreds of millions to billions of years. The prediction was that the very early universe, within the first 500 million years, would contain only the most primitive, chaotic proto-galaxies, irregular blobs, merging fragments, nothing organized, nothing stable. That expectation held for decades because no instrument existed that could observe the universe clearly enough at those epochs to test it. The Hubble Space Telescope, launched in 1990, could see extremely distant objects, but its sensitivity and resolution were insufficient to characterize galaxies in the very early universe in detail. It pushed the frontier, but could not resolve the structure of objects at redshifts above about 10, corresponding to the universe at roughly 500 million years old. Webb changed that. With its 6.5-meter primary mirror, its suite of infrared instruments, and its location at the second Lagrange point 1.5 million kilometers from Earth, in the shadow of a 5-layer sunshield, the size of a tennis court, Webb can observe in wavelengths and with a sensitivity that Hubble could not approach. The first hint that something was wrong with the standard models came quickly within the first year of scientific observations. Webb began finding galaxies at very high redshifts that were unexpectedly bright and unexpectedly massive. Not small, dim proto-galaxies struggling to form, but relatively large, bright objects with populations of mature stars. The number of these galaxies exceeded the predictions of standard cosmological models by factors of 10 to 100 in some analyses. Something was off. Then came the discovery of the galaxy, known by its designation as MOMZ14. This object was identified in data from May 2025. The light reaching Webb from this galaxy left its source when the universe was approximately 280 million years old. For context, the universe is currently 13.8 billion years old, so this galaxy is being observed at a time when the universe was only about 2% of its current age. And yet the galaxy is not a disordered collection of young stars. It is a compact, organized structure approximately 500 light-years across, with a total stellar mass of roughly 100 million times the mass of the Sunday. Those are not the numbers of a proto-galactic cloud. Those are the numbers of a formed galaxy, a small one, but a real one, with structure that required time to develop. The problem this creates is straightforward. Building a galaxy of that mass and organization requires a sequence of physical processes, each of which takes time. Gas must cool and condense. Stars must form, burn for millions of years, and die, seeding the surrounding gas with heavier elements. Gravity must sculpt the growing star cluster into a coherent structure. Even under optimistic assumptions about how quickly these processes can proceed, it is not clear how a galaxy, with the properties of MOMZ14, could have assembled itself within 280 million years of the Big Bang. 280 million years is not a long time on cosmic scales. On Earth, 280 million years ago, dinosaurs had not yet evolved. The supercontinent Pangaea was intact. This period is a substantial fraction of Earth's history, yet it represents only about 2% of cosmic history. In that time, from a universe containing only hydrogen and helium gas, MOMZ14 had to not only form stars, but organize them into a compact, structured galaxy. Either the galaxy formed significantly faster than standard models predict, or the standard models are missing something important about the early universe. Several explanations have been proposed. One possibility is that the first stars formed more rapidly than estimated, seeding early galaxy formation faster than models assumed. If the gas in the early universe cooled more efficiently, or if the dark matter distribution created deeper gravitational wells more quickly, the first generation of stars might have appeared earlier and in greater numbers than current models suggest. A second possibility involves dark matter. The standard model of structure formation assumes that dark matter halos grew gradually, with larger halos forming from the merger of smaller ones over time. But if dark matter had different properties in the very early universe, if it clustered more efficiently, or if its interaction cross-sections were different, it could have provided more concentrated gravitational wells earlier, allowing baryonic matter to collapse faster. A third and more radical possibility is that some aspect of the physics of the early universe was different from what it is today. General relativity and the standard model of particle physics both assume that the fundamental constants of nature, the strength of gravity, the speed of light, the cosmological constant, are fixed. But there are theoretical frameworks in which some of these constants were different in the early universe and have evolved to their current values. If the physics was even slightly different, the timescales for structure formation could have been significantly altered. This last category of explanation is speculative and would require extraordinary evidence. But MOMZ-14 is not the only galaxy that raises these questions. Webb has been accumulating a growing catalogue of early, unexpectedly mature galaxies for over a year. Across multiple observational programs and surveys, the telescope has consistently found more high redshift galaxies, and more massive ones, than the predictions of the standard lambda-CDM cosmological model, the leading model of the universe's composition and evolution, would suggest. MOMZ-14 is currently the most extreme example, the farthest and the earliest, but it sits within a larger pattern of discrepancy between observation and prediction. Cosmologists are working actively to understand whether this discrepancy reflects errors in the models, errors in the observations, or genuine new physics. Some researchers argue that the stellar mass estimates for very distant galaxies may be systematically overestimated, because the methods used to infer mass from observed light depend on assumptions about stellar populations that may not apply to the first generations of stars. Others argue that the observations are robust and the models need revision. This is how normal science operates. At the frontier, data pushes against models. Researchers propose explanations, and the cycle of observation and refinement continues. But MOMZ-14 has pushed harder than most, and the cosmological community is paying close attention. While astronomers were grappling with the implications of galaxies that formed too early, Webb was simultaneously generating a different kind of controversy about a planet far closer to home. The planet is K2-18b, an exoplanet discovered in 2015 by the Kepler Space Telescope. It orbits a red dwarf star called K2-18, located about 124 light-years from Earth in the constellation Leo. The planet orbits in the habitable zone of its star, the range of orbital distances where liquid water could theoretically exist on a planetary surface, and it was known to have a hydrogen-rich atmosphere from earlier observations by Hubble. But K2-18b is not an Earth-like planet in any straightforward sense. It is roughly 2.5 times Earth's diameter and approximately 8.5 times Earth's mass, placing it in a category called sub-Neptunes, or Hycean worlds planets, thought to be covered by deep global oceans beneath thick, hydrogen-rich atmospheres. The conditions on such a world, if one exists, would be very different from those on Earth. In January 2025, a study was published reporting the detection of dimethyl sulfide in the atmosphere of K2-18b, based on observations made by Webb using its near-infrared spectrograph and mid-infrared instrument. Dimethyl sulfide is a sulfur-containing organic compound with the chemical formula consisting of 2 methyl groups bonded to a sulfur atom. On Earth, it is produced almost exclusively by biological processes, primarily by marine phytoplankton and other microscopic ocean-dwelling organisms, when they metabolize a compound called dimethylsulfoniopropanate. Dimethyl sulfide is continuously released from the ocean into the atmosphere, where sunlight and oxidants break it down relatively quickly. Because it is destroyed rapidly, its presence in the atmosphere requires a continuous source. On Earth, that source is life. This is what makes the potential detection of dimethyl sulfide in the atmosphere of K2-18b significant. If confirmed, it would represent the first detection of a biosignature, a chemical compound associated with biological activity in the atmosphere of an exoplanet. The word "if confirmed" is doing important work in that sentence. When Webb analysed the infrared spectrum of K2-18b's atmosphere, measuring how the planet's atmosphere absorbs different wavelengths of light as the planet transits in front of its star, the data showed absorption features consistent with dimethyl sulfide. The signal was not ambiguous to the team that analysed it. It was strong enough to be reported. And when the observations were repeated, the signal appeared again, reportedly at concentrations estimated to be roughly 1,000 times higher than dimethyl sulfide's concentration in Earth's atmosphere. However, the scientific community has been appropriately cautious. Detecting the composition of an exoplanet atmosphere from 124 light-years away is technically extremely challenging. The infrared spectrum contains many overlapping absorption features from different molecules, and distinguishing one from another requires careful modeling and analysis. Some scientists have noted that dimethyl sulfide shares some spectral features with methane, which is also present in K2-18b's atmosphere, and which has a known abiotic source, meaning it can be produced without life. Ruling out methane contamination of the signal is an important step that requires further analysis. There is also the question of whether any abiotic process could produce dimethyl sulfide at such high concentrations. On Earth, no such process is known, but K2-18b is not Earth. Its atmosphere is hydrogen-rich rather than nitrogen-oxygen dominated. Its surface, if it has a liquid water ocean, is under very different pressure and chemical conditions than Earth's oceans. There may be geochemical processes on such a world that have no equivalent on Earth, and that could in principle produce organic sulfur compounds abiotically. This has not been demonstrated, but neither has it been ruled out. The appropriate scientific position is that the signal is intriguing and significant, that it warrants further investigation, and that no conclusion about its biological or abiotic origin is yet justified. The teams involved in the observations have stated this explicitly. Further observations with Webb, and potentially with other instruments, including the proposed European Extremely Large Telescope and other next-generation ground-based facilities, will provide better data from which stronger conclusions can be drawn. What the detection does establish, regardless of its ultimate explanation, is that Webb is capable of detecting organic molecules in the atmospheres of planets, in the habitable zones of nearby stars. This capability, demonstrated here, opens the door to a systematic program of biosignature searches across many exoplanet targets. K2-18b may ultimately prove not to harbour life. But the detection method it has demonstrated is one that will be applied to dozens or hundreds of other planets in the years ahead. The broader context matters here. In the decades since the Kepler mission began returning data on exoplanet populations, astronomers have established that Earth-sized and near-Earth-sized planets are extremely common in the Milky Way. Estimates suggest there are tens of billions of rocky planets in the habitable zones of their stars in the galaxy alone. The universe is full of potentially life-bearing worlds, or at least of worlds where the physical conditions are not immediately hostile to the chemistry of life as we understand it. What had been missing was the ability to actually look at these planets in any meaningful detail. Kepler detected them through the transit method, measuring the tiny dip in starlight as a planet passes in front of its star, but it could not characterize their atmospheres. Webb, with its unprecedented sensitivity in the infrared, can actually probe atmospheric chemistry. K2-18b is one of the first results of applying that capability directly to the question of biosignatures. Alongside the galaxy formation anomalies and the potential biosignature on K2-18b, Webb produced a third category of surprising result: detailed observations of Neptune. Neptune is the outermost major planet in the solar system, orbiting the Sun at an average distance of 30 astronomical units, 30 times the distance from Earth to the Sunday. It is a cold, dark ice giant with a complex atmosphere of hydrogen, helium, and methane, the last of which gives it its distinctive blue colour. Despite being known since its discovery in 1846, Neptune has been visited by spacecraft only once, by Voyager 2 in August 1989, during its grand tour of the outer solar system. The Voyager 2 flyby provided the first close-up images of Neptune, revealing its deep blue colour, its large dark storm system, the Great Dark Spot, analogous to Jupiter's Great Red Spot and its largest moon, Triton. But the encounter lasted only hours. The data collected was extraordinary for its time, but it represented a single snapshot of a single moment in the planet's long-term behavior. In the decades since, Neptune has been studied from a distance using ground-based telescopes and occasionally by space telescopes not specifically designed for planetary science. Webb changed that picture dramatically when it turned its instruments toward Neptune. The observations were made with Webb's near-infrared camera, which images at wavelengths invisible to the human eye, but highly revealing for planetary science. At these wavelengths, methane in Neptune's atmosphere absorbs light strongly, which means regions of the atmosphere where methane is present appear dark in the images. Regions where high-altitude clouds of frozen methane particles reflect sunlight before it can be absorbed appear very bright. The images revealed Neptune's ring system with a clarity and detail never previously achieved from Earth. Neptune has rings, 5 main rings, less prominent than Saturn's but real, and they had been difficult to observe previously because of the brightness of the planet itself relative to the faint ring material. Webb's infrared sensitivity, combined with its position in space, away from Earth's atmosphere, provided a clean enough view to resolve the rings and their structure. But the more scientifically significant result involved Neptune's auroras. Auroras on Neptune had been theoretically predicted, but never directly detected before Webb's observations. On Earth, auroras, the northern and southern lights, are produced when charged particles from the solar wind, a continuous stream of particles from the Sun, are funneled by Earth's magnetic field toward the polar regions. When these particles collide with molecules in the upper atmosphere, they excite those molecules, which then release energy as light. Neptune has a magnetic field, but it is unusual in a way that makes aurora physics on Neptune very different from Earth. Earth's magnetic field is roughly aligned with the planet's rotation axis. The magnetic pole is close to the geographic pole. Neptune's magnetic field is tilted by approximately 47 degrees from its rotation axis, and its magnetic center is offset from the planet's geometric center by a substantial fraction of the planet's radius. This means that as Neptune rotates, its magnetic field wobbles dramatically relative to the planet's surface, creating a highly variable and chaotic pattern of magnetic interaction with the solar wind. The consequence is that auroras on Neptune are not confined to the polar regions as they are on Earth. They can appear at almost any latitude, shifting position as the planet rotates. They are also powered by solar wind that has been traveling for 4.5 hours at typical solar wind speeds to reach Neptune's distance, and has expanded and cooled considerably during that journey. Webb's infrared observations detected emission from trihydrogen cation, a molecular ion consisting of 3 hydrogen atoms with a positive charge, formed when solar wind particles ionize hydrogen in the upper atmosphere at multiple locations across Neptune's disk. This emission is the signature of auroral activity. The spatial distribution was consistent with the complex, tilted, magnetic field structure and showed that auroras were occurring across a wide range of latitudes simultaneously. The temperature data from the same observations revealed another puzzle. Across Neptune's atmosphere, temperature varied in ways that were not fully explained by the distribution of sunlight, which, at Neptune's distance, provides very little heating anyway. Some regions were cooling faster than expected. Other regions showed elevated temperatures without an obvious energy source. One possibility is that the auroral activity itself is depositing energy into the upper atmosphere in ways that affect temperatures at lower altitudes. Another possibility involves wave dynamics within the atmosphere, atmospheric waves that propagate upward and deposit their energy as heat at high altitudes. A third possibility is that Neptune has more internal heat than current models assume, with some fraction of that heat being deposited non-uniformly in the atmosphere. Neptune is known to radiate significantly more heat than it receives from the Sun, roughly 2.6 times as much. This excess heat comes from the planet's interior, left over from its formation approximately 4.5 billion years ago. But how that heat moves through the planet's interior and atmosphere, and whether that movement has observable effects on atmospheric temperature patterns, is not well understood. Webb's Neptune observations thus provided both answers and new questions. The auroras, confirmed for the first time, validate theoretical models of how Neptune's tilted magnetic field interacts with the solar wind. The temperature anomalies, on the other hand, require explanation and are motivating new modelling efforts. Neptune's moons also received attention. Triton, the largest and most studied of Neptune's 14 known moons, is one of the most geologically unusual objects in the solar system. It orbits Neptune in the opposite direction from the planet's rotation, a retrograde orbit that strongly suggests it was not formed alongside Neptune, but was captured from the Kuiper belt at some point in the solar system's history. Its surface is covered with a pinkish nitrogen ice, and Voyager 2 detected active geysers erupting nitrogen gas from the surface. It is one of the few places in the solar system with confirmed active geological processes. Webb was not the primary instrument for the Neptune moon observations, but its sensitivity allowed detection of Triton's thermal emission with a precision useful for constraining models of its interior and surface composition. Combined with the Neptune atmospheric data, these results are building a more complete picture of the Neptune system than anything available since Voyager 2's brief flyby. The Neptune results illustrate a point that is sometimes overlooked when discussing Webb's capabilities. The telescope was primarily designed for extragalactic and high redshift astronomy, but its extraordinary sensitivity and infrared wavelength coverage make it a powerful tool for solar system science as well. Objects that are bright enough to saturate its instruments, the Sun, the inner planets, require special observing strategies or are simply off-limits. But the outer planets, their moons, and the smaller bodies of the outer solar system are accessible targets, and Webb's observations of them have already produced results that simpler, more traditional telescopes could not. The combination of discoveries coming from Webb across these different observational categories, early galaxy formation, potential biosignatures, planetary atmospheres, reflects something about how large, powerful instruments function at the frontier of science. They do not simply confirm what is already known with better precision. They reveal things that were genuinely unknown, not because scientists failed to imagine them, but because no previous instrument was sensitive enough to detect them. The galaxy MOM-Z14 was not predicted to exist by any model, but it was not imagined to be impossible either. It simply could not be observed before Webb. The dimethyl sulfide signal from K218b was something that planetary scientists had discussed as a theoretical possibility for a hypothetical future instrument, and Webb has become that instrument. Neptune's auroras had been predicted theoretically, but without the sensitivity to detect them, they remained hypothetical. In each case, the discovery arrived because the tool finally matched the scale of the question. This matters for how the field will develop. Webb is designed for a lifetime of at least 10 years, and ideally 20. The observations so far represent a relatively small fraction of the total scientific program. Survey projects designed to characterize large samples of early galaxies, comparative studies of multiple exoplanet atmospheres, and systematic monitoring of solar system targets are all underway or planned. The individual discoveries reported so far are not the culmination of Webb's program, they are the early results. What can reasonably be expected in the years ahead? In cosmology, the catalogue of very high redshift galaxies will grow substantially. Better statistics on how many such objects exist at different epochs will constrain models of early galaxy formation more tightly. If the excess of massive early galaxies holds up as the sample grows, the pressure on standard cosmological models will increase, and theorists will be pushed toward more significant modifications. The nature of the first stars, still not directly observed, may come within Webb's observational reach with deeper surveys. In exoplanet atmospheric science, the K2-18b result will be followed by observations of other Hycean world candidates. There are several known sub-Neptune planets in the habitable zones of nearby stars that are suitable targets for Webb's transit spectroscopy capability. Some of these targets, including planets orbiting TRAPPIST-1, a star just 40 light-years away, with 7 known rocky planets, have already been observed by Webb, with results that include detection of carbon dioxide in at least some planetary atmospheres. As observations accumulate, the presence or absence of potential biosignatures across multiple targets will provide statistical context for interpreting any individual detection. In solar system science, Webb will continue to provide unprecedented views of the outer planets and their moons, contributing to the scientific preparation for planned future missions. The proposed Uranus Orbiter and Probe mission, currently in early planning stages, would study an ice giant that Webb has already observed in some detail. Webb's characterization of Uranus's atmosphere and ring system complements what a future in situ mission would provide. There is also a broader theme in all of this that extends beyond any individual discovery. The universe, as Webb is revealing it, is a more active and complex place than the dominant models assumed before the telescope began operating. The early universe formed structure faster than expected. Some planets in habitable zones may harbor chemistry associated with life. Even familiar solar system planets contain atmospheric and magnetic phenomena that were previously unresolved. In each case, the complexity was always there. Webb did not create it. What the telescope has done is provide the sensitivity and wavelength coverage needed to detect it. The universe was always building galaxies faster than models predicted in the era when no instrument could test those predictions. K2-18b always had whatever chemistry it has in its atmosphere. Neptune always had auroras. What changed is that we can now see these things. That change has a specific meaning in the context of the search for life in the universe. For most of the history of this question, the absence of evidence for life beyond Earth was interpreted by some as weak evidence of absence. The universe seemed quiet. The sky seemed empty. The inference, however cautious and hedged, was that perhaps life was rare, perhaps Earth was unusual, perhaps the emergence of biology required conditions so specific that they were unlikely to occur elsewhere. Webb is systematically eroding the observational basis for that inference. It is not proving that life exists elsewhere. The K2-18b result does not prove that, and scientific caution requires treating it as unconfirmed until many more observations and analyses have been done. But it is demonstrating that the chemistry of life is not confined to Earth in any obvious way. Organic molecules are common throughout the galaxy. Habitable zone planets are abundant. The physical conditions for life, whatever they turn out to be precisely, are not as rare as the silence of the pre-Webb era implied. The parallel track of early galaxy formation research tells a complementary story. If galaxies, like MOM-Z14, formed within the first 300 million years of cosmic history, and if some of those galaxies achieved a stability similar to what we see in more mature systems relatively quickly, then the window of cosmic history during which life could in principle have emerged is longer than previously assumed. Life requires stable environments. If stable galactic environments existed earlier than we thought, the earliest possible epoch of life in the universe may be pushed significantly back. This is speculative reasoning, connecting the formation of early galaxies to the potential emergence of life is many steps removed from direct observation. But it illustrates how the different threads of Webb's discoveries are connected by a common underlying question about the place of complex chemistry and biology in the universe's history. What remains unknown is substantial. The origin of the excess of massive early galaxies has not been explained. The K2-18b signal has not been confirmed by independent observations, and its interpretation remains actively debated. Neptune's temperature anomalies have no accepted explanation. The nature of the first stars, crucial for understanding early galaxy formation, has not been directly observed. The physical conditions on Hycean worlds like K2-18b, which determine whether any detected chemistry is biological or abiotic, are poorly constrained. These open questions are not gaps that will remain unfilled indefinitely. They are the specific targets of ongoing and planned research programs. Theoretical cosmologists are developing revised models of early structure formation that can be tested against the growing catalogue of high redshift observations. Planetary scientists are building models of Hycean world chemistry to understand what biosignatures would and would not be expected from abiotic processes in such environments. Atmospheric physicists are modelling Neptune's energy budget to understand the sources of its observed temperature variations. Science advances through this iterative cycle. Observation reveals unexpected phenomena, theory proposes explanations, new observations test those explanations, and understanding gradually improves. Webb has substantially accelerated the rate of input to this cycle by providing observations of unprecedented quality across multiple fields simultaneously. The telescope will continue operating, accumulating data, and confronting the models with new measurements. Each new observation cycle brings the possibility of new surprises, another galaxy that is too early, another planet with unexpected atmospheric chemistry, another solar system object that turns out to be more complex than it appeared. What is already clear, even at this early stage in Webb's scientific program, is that the picture of the universe it is drawing looks different from the one that preceded it. The early universe built structure faster than expected. Some planets in the habitable zones of nearby stars may harbour chemistry associated with life. The solar system's familiar outer planets contain phenomena that were genuinely unknown until the right instrument pointed at them. Each of these results is individually important. Together, they are beginning to outline a universe that is richer, more complex, and more actively evolving than the models built before Webb could test them. That outline will become clearer with more observations. But its broad shape is already visible. The universe, it turns out, has been busy. It was forming galaxies, while the standard models said it was still preparing the conditions. It may have been hosting chemistry associated with life in places where we had no reason to look. It was generating auroras on a tilted, distant ice giant that no one had yet confirmed because no instrument was sensitive enough to detect them. Webb did not change the universe. It changed what we can see of it. And what it is showing us is that the universe we could not yet see was far more active than the one we thought we knew. The open questions that remain are not signs of failure. They are signs that the field is working correctly, that new observations are pushing against old models and creating productive scientific tension that will drive the next generation of discoveries. Webb will continue to be the primary instrument generating that tension for at least the next decade. The results coming from it in the years ahead will shape the scientific questions of the generation that follows. For now, the observations are accumulating, the models are being revised, and the universe is continuing to be, as it has always been, more complicated and more interesting than anyone predicted. The story of how Webb came to exist is itself worth understanding, because it illuminates why its discoveries are so different in character from what came before. The telescope's development began in the mid-1990s, when NASA began planning what it initially called the Next Generation Space Telescope. The design process stretched over more than 2 decades, driven by the need to address specific scientific questions that Hubble had raised but could not fully answer. Hubble had found that the universe was expanding at an accelerating rate. It had detected galaxies at very high redshifts, but could not characterize them well enough to test models of early galaxy formation. It had found evidence for the common occurrence of exoplanets, but could not study their atmospheres. Answering these questions required a fundamentally different kind of observatory, one that observed primarily in infrared wavelengths. The reason for infrared is the redshift of the universe. Light from the most distant galaxies, those in the very early universe, was emitted at ultraviolet and visible wavelengths. But as that light has traveled through the expanding universe for 13 billion years, the expansion has stretched its wavelengths, shifting it into the infrared range. Hubble, with its primary sensitivity at visible and ultraviolet wavelengths, could not efficiently observe these redshifted galaxies. Webb, with infrared instruments tuned to wavelengths between about 1 micrometer and 28 micrometers, can. The same infrared sensitivity that makes Webb ideal for observing distant galaxies also makes it powerful for exoplanet atmospheric spectroscopy. When an exoplanet transits in front of its star, some of the starlight passes through the planet's atmosphere before reaching the telescope. Molecules in the atmosphere absorb specific wavelengths of light, creating a pattern of absorption features in the spectrum that identifies which molecules are present. Many biologically relevant molecules, water, carbon dioxide, methane, dimethyl sulfide, have their primary absorption features in the infrared range that Webb covers. This dual utility was not entirely coincidental. The scientific requirements that shaped Webb's design included both early universe observations and exoplanet atmosphere characterization, because both required infrared wavelength coverage at high sensitivity. The result is a telescope that excels at both simultaneously an observational tool whose capabilities align with the most important, outstanding questions in multiple fields of astrophysics. The technical challenges of building Webb were substantial. The mirror needed to be large enough to collect sufficient light from the faintest and most distant sources, but light enough to be launched on a rocket and deployed in space. The solution was a segmented mirror, 18 hexagonal segments of beryllium, each coated with a microscopically thin layer of gold that could be folded for launch and then unfolded and precisely aligned once in space. The alignment process, completed in early 2022, brought the 18 segments into focus with an accuracy measured in nanometers. The instruments needed to operate at extremely low temperatures, some of them close to absolute zero, because any thermal emission from the telescope itself would swamp the faint signals from distant galaxies and cold exoplanet atmospheres. The sunshield, made of a thin, highly reflective material, keeps the telescope in the shadow of the sun and allows the instruments to passively cool to the temperatures needed for operation. The mid-infrared instrument, which requires the coldest operating temperature of any Webb component, uses an active cooling system to reach approximately 6.5 degrees above absolute zero. The telescope was launched on December 25, 2021, on an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana. After launch, it spent approximately a month traveling to its operational position, the second Lagrange point, or L2, unfolding the sunshield and the mirror segments during the journey. The mirror alignment and instrument commissioning took several more months. First science results were released in July 2022, and regular scientific observations have been ongoing since. The data from Webb goes through a pipeline of calibration and reduction before it is available for analysis. The telescope observes targets selected from scientific proposals submitted by researchers worldwide, evaluated through a competitive review process similar to that used for other major observatories. This means that Webb's observing time is allocated across a wide range of scientific programs, from studies of the most distant galaxies to observations of asteroids in our own solar system. Understanding this allocation context helps clarify why the discoveries covered here are not the result of a single focused program. K218b was observed as part of a program on Hysian world atmospheric characterization. MOMZ-14 was identified in a high redshift galaxy survey. Neptune was observed as part of a solar system program studying outer planet atmospheres. Each discovery came from a different scientific program, designed to address a different set of questions, and they arrived independently. That independence makes the common theme more striking. These are not cherry-picked examples chosen to support a narrative. They are results from different research programs, targeting different objects using different instruments, analyzed by different research teams. And yet they all share a common characteristic. They revealed something about the universe that the models did not predict, or revealed it with a clarity that fundamentally changes how scientists think about it. Galaxies that should not have formed yet, atmospheric chemistry on a distant planet that on Earth is produced by life, aurora activity on Neptune that confirms theoretical predictions while generating new questions about the planet's energy balance. The common thread is not the subject matter, it is the gap between expectation and observation. This gap is scientifically productive. Science advances not when observations confirm what is already known, but when they reveal something unexpected that requires explanation. Each of Webb's surprising discoveries is a puzzle that needs solving, and solving puzzles requires new ideas, new models, and often new observations. The scientific activity generated by these discoveries, the papers published, the models revised, the follow-up observations proposed, is the mechanism by which understanding actually advances. The field of exoplanet atmospheric science, for instance, has been transformed by Webb's capabilities in ways that go beyond the K2-18b result. Before Webb, the ability to characterize exoplanet atmospheres was largely limited to detecting very abundant molecules, primarily water vapor and carbon dioxide, in the atmospheres of relatively close, large planets transiting bright stars. The detection of minor trace gases, including potential biosignatures, was considered a goal for future, larger instruments. Webb has already detected carbon dioxide, sulfur dioxide, water vapor, methane, and carbon monoxide in various exoplanet atmospheres. Each detection provides constraints on the temperature, pressure, chemistry, and formation history of the planet. The detection of sulfur dioxide in the atmosphere of a hot Jupiter, a large gas giant orbiting very close to its host star in 2023, was the first detection of a photochemical product in an exoplanet atmosphere, providing direct evidence that photochemistry driven by stellar radiation shapes atmospheric composition in real exoplanets, not just in models. These detections are building a vocabulary for interpreting exoplanet atmospheres. When scientists look at a spectrum from a planet in the habitable zone, they need a framework for understanding which molecules are expected from abiotic chemistry and which would require biology to explain. Building that framework requires studying many different planets in many different environments, developing models of their chemistry, and testing those models against observations. Webb is providing both the observations and the motivation to build better models. The detection of dimethyl sulfide in K2-18b's atmosphere, if confirmed, will fit into this growing framework. It will raise the question of what combination of chemistry, biological, or abiotic can explain the full atmospheric profile of the planet. Answering that question will require not just more observations of K2-18b, but better models of Hycean world atmospheric chemistry that can be tested against the observations. Several theoretical groups are already working on models of Hycean world chemistry, attempting to identify which molecules would be present at what concentrations under purely abiotic conditions, and which would require biological sources to explain. This work is difficult because the conditions on a Hycean world, a deep global ocean under a hydrogen-rich atmosphere, in the habitable zone of a red dwarf star, have no direct analogue in the solar system. Earth's oceans, Venus's surface, and Mars's ancient surface are all invoked for partial analogies, but none captures the full combination of conditions. The specific star type matters too. Red dwarf stars, which K2-18 is, are the most common type of star in the galaxy. They are smaller, cooler, and less luminous than the Sunday. They emit proportionally more radiation at infrared and near-infrared wavelengths, and less at ultraviolet wavelengths. A planet in the habitable zone of a red dwarf orbits much closer to its star than Earth does to the Sun, because the star is dimmer and the habitable zone is correspondingly closer in. This proximity has implications for the planet's tidal locking, the tendency of close-orbiting planets to have one face permanently turned toward the star, and for the intensity of high-energy radiation and stellar wind impacting the planet. Some researchers have argued that red dwarf stars are poor hosts for habitable planets, precisely because of these factors. Intense stellar flares from young red dwarfs can strip planetary atmospheres. Tidal locking could create extreme temperature differences between the day and night sides of a planet. The lack of ultraviolet radiation might impede the chemistry that some models of life's origin require. Others have argued the opposite, that red dwarfs, precisely because of their long lifespans of tens to hundreds of billions of years, provide stable environments for life to emerge and evolve over very long timescales. A planet in the habitable zone of a red dwarf has more time than Earth had potentially much more to develop complexity. If life requires only that conditions be stable and energy sources available, the long lifespans of red dwarfs could make them ideal for hosting biology. K2-18b sits in the middle of this debate. Its star is a red dwarf. It is in the habitable zone. It may or may not show a biosignature. Whatever the ultimate interpretation, it is one of the most important test cases for understanding habitability around the most common type of star in the galaxy. The early galaxy formation questions raised by Webb also connect to habitability in ways that are less obvious but real. Life, as we understand it, requires not just a stable environment and liquid water. It requires a specific set of heavier elements: carbon, nitrogen, oxygen, phosphorus, sulfur, that were not present in the early universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. All the heavier elements that make up planets, oceans, and biology were synthesized in stars and distributed by stellar explosions. The first generation of stars, the population 3, stars that formed in the very early universe, had no heavier elements at all. They were made of pure hydrogen and helium. They could not form the kind of rocky planets that bear life. They could not form any planet at all, in fact, in the traditional sense, because planet formation requires solid material, which requires elements heavier than helium. It took multiple generations of stars forming, living, dying, and seeding the next generation with their processed material before the chemical conditions for planet formation and potentially life were met. This is one reason why the very early universe is generally considered unlikely to have hosted life, regardless of how many galaxies existed. But how early is early enough? When did the universe's chemical enrichment, driven by successive stellar generations, reach the threshold needed for rocky planet formation and biological chemistry? Some estimates suggest that by around 1 billion years after the Big Bang, some regions of some galaxies had accumulated enough heavy elements from early supernovae to potentially host rocky planets. The galaxies where this could have happened were probably the most massive ones, which formed stars earliest and produced the most enrichment per unit time. If structures like MOM-Z14 hosted not only stars, but also processed those stars through their full life cycles within the first few 100 million years, then the chemical enrichment in those galaxies may have reached planet-forming thresholds earlier than standard models assumed. This is speculative. There are many steps between the existence of a compact early galaxy and the formation of rocky planets within it. But MOM-Z14 is part of a growing dataset that suggests the early universe was chemically active earlier than previously thought. which pushes the earliest possible epoch of rocky planet formation, and therefore potentially of life, further back in cosmic history. The James Webb Space Telescope is not the only instrument contributing to these questions. It is the most powerful currently operating, but it functions within a broader infrastructure of astronomical facilities that provide complementary capabilities. The Atacama Large Millimeter Array in Chile, an international radio telescope facility consisting of 66 high-precision antennas, observes at millimeter and submillimeter wavelengths. It can detect the cold dust and molecular gas that are the raw material for star and planet formation in distant galaxies, providing a view of the universe that is complementary to Webb's infrared vision. Observations of early galaxies with the Atacama Large Millimeter Array have revealed the gas reservoirs feeding star formation at high redshifts, contributing to the picture of how the first galaxies built up their stellar populations. The Very Large Telescope in Chile, operated by the European Southern Observatory, provides spectroscopic capabilities at optical and near-infrared wavelengths that complement Webb's broader wavelength coverage. Follow-up spectroscopy of galaxies and exoplanets initially characterized by Webb allows astronomers to determine precise redshifts, chemical abundances, and stellar population properties with high accuracy. The Chandra X-ray Observatory and the XMM Newton X-ray Telescope provide X-ray observations of high-energy phenomena, the hot gas in galaxy clusters, the emission from black holes, the energetic processes associated with stellar activity that are invisible to infrared telescopes like Webb. X-ray observations of nearby stars provide constraints on the high-energy radiation environment experienced by their exoplanet companions, which affects atmospheric stability and potential biosignature interpretation. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey large areas of sky with infrared sensitivity comparable to Webb's, but with a much wider field of view. Where Webb is optimized for deep, detailed observations of specific targets, Roman is designed for wide area surveys that will produce statistical samples of galaxies, exoplanets, and dark matter distributions that individual deep observations cannot provide. Roman will complement Webb by providing the large samples needed to understand the significance of individual surprising discoveries in a broader context. On the ground, the extremely large telescope, currently under construction in Chile, with a primary mirror 39 meters in diameter, will provide spatial resolution and light collecting capability that exceeds current instruments by factors of 5 to 10. When it enters operation in the late 2020s, it will be able to directly image some exoplanets and characterize their spectra in ways currently impossible, potentially providing independent confirmation or refutation of biosignature detections from Webb. This constellation of current and upcoming facilities is being coordinated to address the specific scientific questions that Webb has sharpened. The discovery of dimethyl sulfide in K218b's atmosphere will motivate follow-up programs on multiple telescopes. The discovery of MOMZ-14 will feed into a broader program of high redshift galaxy characterization using multiple instruments. The Neptune observations will contribute to the scientific preparation for future outer planet missions. Science at this scale is international and collaborative. The research papers describing Webb's discoveries typically list dozens to hundreds of co-authors from institutions across multiple countries. The data from Webb is available to researchers worldwide through public archives, allowing scientists who were not part of the original observing programs to analyze the data and propose new interpretations. This open access model accelerates the pace of discovery by maximizing the number of people applying analytical skills to the available information. The pace of discovery from Webb over its first few years of operation has been faster than many astronomers anticipated. The rate of surprising findings, the early massive galaxies, the potential biosignature, the Neptune auroras reflects both the telescope's extraordinary capabilities and the fact that those capabilities were applied to questions where the existing models had not been well tested by observation. There are more such questions waiting. The atmospheres of rocky planets in the habitable zones of nearby stars remain largely uncharacterized. The detailed structure and chemistry of the very first galaxies is still being mapped. The moons of the outer planets, many of which may harbor subsurface liquid water, have barely been studied by Webb. The cold molecular clouds where stars are currently forming, the disks of gas and dust around young stars where planets are assembling, the chemical composition of comets in the outer solar system, all of these are targets that Webb will address in its continuing observing program. Each of these targets holds the potential for the kind of unexpected result that drives fields forward. Science at the frontier is always partly about expecting the unexpected building instruments capable of detecting phenomena that have not been seen before and being willing to revise understanding when those instruments reveal something the models did not predict. Webb has demonstrated, repeatedly and across multiple fields, that such revisions are waiting to be made. The universe, observed at the sensitivity and wavelength coverage that Webb provides, looks different from the universe observed by previous instruments. Not completely different, the basic physical laws that govern it are the same, but the richness of the phenomena those laws produce, at the scales Webb can now access, has surprised nearly everyone who has worked with its data. The coming years of Webb observations will continue to deliver surprises. Some of those surprises will challenge existing models in ways that require significant revision. Others will fill in gaps in the existing framework without overturning it. A few may point toward genuinely new physics, though extraordinary claims of this kind require extraordinary evidence, and the scientific community rightly applies high standards of scrutiny to such proposals. What is certain is that the universe is more complex than any model built before Webb had access to its current observational reach. The discoveries covered here are the early chapters of a story that will continue to develop for at least another decade of Webb observations, supplemented by the capabilities of new instruments as they come online. The full picture of what Webb has revealed will take years to assemble, but the outline is already visible: an early universe that built structure faster than expected, a planet with atmospheric chemistry that warrants serious scientific attention, an ice giant in our own solar system with confirmed auroral activity and unexplained atmospheric temperature variations. None of these discoveries was anticipated in the form it arrived. All of them point toward a universe that rewards closer examination with deeper complexity. That is what telescopes have always done. Webb is doing it on a scale and with a precision that was not previously possible. The results are changing what we know, what we do not know, and which questions are worth asking next. To appreciate how far observational astronomy has come, and what Webb represents as a culmination of that progress, it helps to trace the history of how we have understood the universe's large-scale structure. The concept of a galaxy as an independent system of billions of stars, similar to the Milky Way but vastly distant, was not universally accepted until the 1920s. Before that, the fuzzy patches of light, called nebulae, in early telescopic observations were debated. Some astronomers argued they were distant galaxies, others that they were clouds of gas within the Milky Way. The debate was resolved by Edwin Hubble's measurements in 1924 and 1925, when he used Cepheid variable stars as distance indicators to show that several spiral nebulae were much too far away to be within our galaxy. They were independent galaxies in their own right. Hubble also discovered that most galaxies are moving away from us, with recession velocities proportional to their distances to the observational basis for the expanding universe, and, by extrapolation backward in time, for the Big Bang theory. Later, Vesto Slipher had actually first measured the recession velocities of spiral nebulae, but it was Hubble's combination of distance and velocity measurements that established the expansion relationship. The Big Bang theory itself, the idea that the universe began in an extremely hot, dense state and has been expanding ever since, was developed theoretically by Georges Lemaitre and others in the 1920s and 1930s, and was confirmed observationally by Arno Penzias and Robert Wilson's accidental discovery of the cosmic microwave background radiation in 1965. The cosmic microwave background is the thermal afterglow of the hot early universe, predicted by Big Bang theory and observed as a nearly uniform microwave radiation coming equally from all directions in the sky. The cosmic microwave background has been studied in exquisite detail by a series of satellites: the Cosmic Background Explorer in the early 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite in the 2010s. These missions mapped tiny temperature variations in the background radiation, fluctuations of about 1 part in 100,000 from the average temperature that represent the seeds of all subsequent structure in the Makic universe, where the background was slightly warmer, matter was slightly denser, and gravity would pull more material in, eventually forming the first stars and galaxies. The parameters of the standard cosmological model, the density of dark matter, the density of ordinary matter, the cosmological constant, the rate of expansion have been measured with precision by these background radiation surveys and by other probes including Type Ia supernovae, galaxy surveys, and gravitational lensing measurements. The model is internally consistent and agrees well with a wide range of observations. It is this well-tested model that Webb is stressing. The model's predictions for the number and properties of galaxies at high redshift were derived from the same physical framework that successfully explained the cosmic microwave background, the expansion history of the universe, and the large-scale distribution of galaxies. When Webb finds galaxies that the model did not predict, it is not challenging some fringe theory. It is challenging the best constrained model of cosmic structure formation that exists. This is why the early galaxy discoveries carry such weight. They are not anomalies in an uncertain framework. They are anomalies in a framework that has been tested and verified across many independent probes. Revising it requires careful analysis and strong evidence. The analysis being done now focuses on several possibilities. One is that the stellar mass estimates for high redshift galaxies, inferred from their light, are systematically too high. The light from a galaxy reflects the total stellar population, but converting light to mass requires assumptions about the age and composition of the stars. If early galaxies had different stellar populations than expected, for instance, if they contained more massive, hotter stars, their light-to-mass ratio would be different, and current mass estimates could be overestimates. Another possibility is that the galaxies are not as massive as they appear, but are simply unusually bright because they are forming stars at very high rates. A galaxy forming stars at 10 or 100 times the normal rate will be much brighter per unit mass than a typical galaxy. If the very early universe contained many galaxies in brief but intense bursts of star formation, they could appear as unexpectedly bright objects in surveys, even if their total mass was within the range predicted by models. A third possibility, which many cosmologists take seriously, is that the standard model's predictions for early galaxy formation are simply wrong, that the model underpredicts how efficiently matter collapsed and formed stars in the early universe. This could reflect a problem with how dark matter is modeled, a problem with how feedback from supernovae and black holes is modeled, or something more fundamental. No consensus has yet emerged, because the data are still accumulating and the analyses are ongoing. This is a genuinely open scientific question, and the outcome will determine whether the Lambda CDM model needs minor adjustment, significant revision, or something more substantial. The exoplanet science context for the K2-18b discovery also has a rich history that shapes how the result is being interpreted. The existence of planets around other stars was confirmed definitively in 1995, when Michel Mayor and Didier Queloz discovered a Jupiter-sized planet orbiting the nearby star 51 Pegasi using the radial velocity method, measuring the tiny wobble a planet induces in its host star's motion along the line of sight. This discovery, which eventually earned a Nobel Prize in Physics in 2019, demonstrated that planetary systems were not unique to the solar system. The Kepler mission, launched in 2009, transformed the study of exoplanet populations by continuously monitoring the brightness of more than 150,000 stars simultaneously, looking for the tiny dips in brightness caused by transiting planets. Over 9 years of operation, Kepler confirmed the existence of more than 2,500 exoplanets and candidate systems. The statistical analysis of the Kepler data established that planets are common throughout the galaxy. Essentially every star, on average, has at least one planet orbiting it. Kepler also characterized the distribution of planet sizes. Rocky planets, smaller than about 1.5 times Earth's diameter, are the most common type. There is a paucity of planets with radii between about 1.5 and 2 times Earth's radius, a feature called the radius gap, above which planets tend to have thick, gaseous envelopes rather than thin, rocky atmospheres. K2-18b, at 2.5 times Earth's diameter, sits above this gap and is thought to have a substantial hydrogen-rich atmosphere, making it a prime candidate for the Haitian world category. The Haitian world concept was developed and named by Niku Madhusudhan and colleagues at the University of Cambridge. The idea is that a sub-Neptune planet in the habitable zone of a star could, under the right conditions, maintain a liquid water ocean beneath a hydrogen-rich atmosphere. The high pressure at the ocean-atmosphere interface would keep water liquid even at temperatures somewhat above water's normal boiling point, because pressure raises the boiling point. The hydrogen-rich atmosphere would act as a greenhouse blanket, maintaining surface temperatures in the range where liquid water is stable. Whether real planets match this theoretical description is an open observational question. K2-18b is the most studied candidate, but it is still poorly characterized in detail. The water ocean, if it exists, cannot be directly observed. Its presence is inferred from the planet's density and compositional modeling. The atmospheric chemistry, including the dimethyl sulfide signal, is what Webb can observe directly. The significance of the Haitian world concept for astrobiology is that such planets might be much more habitable than they superficially appear. A planet covered in a deep ocean, with no land masses and a hydrogen-rich atmosphere, would support very different life from Earth's, if it supports any at all. But the key ingredient for life as we understand it, liquid water, would be abundantly present, at least in the modelled version of these worlds. The search for life in the universe has historically focused on Earth-like conditions: rocky planets, thin nitrogen-oxygen atmospheres, liquid water on the surface, proximity to sun-like stars. Webb's capabilities are expanding the search to include a wider range of environments. Haitian worlds are one such environment. Planets orbiting red dwarf stars, which are very different from the Sun in their radiation output and activity level, are another. The detection of carbon dioxide and other molecules in the atmospheres of planets orbiting red dwarfs has already been achieved by Webb, establishing that atmospheric characterization in such systems is feasible. This broadening of the search is scientifically important because it removes assumptions. If life can only exist in Earth-like conditions, the search is restricted to rocky planets in the habitable zones of Sun-like stars, a relatively small fraction of the galaxy's planet population. But if life can emerge in a wider range of environments, including ocean worlds under hydrogen-rich atmospheres orbiting red dwarf stars, then the potential habitat for life in the galaxy is much larger. K2-18b is, in this broader context, not just a possible location for life. It is a test case for the scientific framework being used to search for life. If the dimethyl sulfide signal is confirmed and ultimately attributed to biology, it will validate the approach of searching for biosignatures in the atmospheres of Haitian worlds. If the signal turns out to have an abiotic explanation, It will refine the framework by identifying a false positive that needs to be accounted for in future searches. Either outcome advances the science. And this is generally true of the Webb discoveries discussed here. Even the null results, the cases where a detection turns out to have a conventional explanation, are scientifically informative. They constrain the models, calibrate the methods, and improve the ability to interpret future observations. The question of whether we are alone in the universe is one of the oldest and most deeply felt questions in science and human culture. For most of history, it could only be addressed by speculation. Telescopes, beginning with Galileo's in 1609, began to make it a scientific question rather than purely a philosophical one. But for centuries, even powerful telescopes could only observe the gross properties of planets in the solar system and nothing about planets elsewhere. The detection of exoplanets in the 1990s transformed the question. It established that the material conditions for planetary systems are common. The Kepler mission established that Earth-sized planets are common. Webb is now establishing that the atmospheric characterization of potentially habitable planets is observationally feasible. Each step has brought the question closer to being answerable by observation rather than speculation. The search is not over, and a definitive answer, confirmed detection of biological activity on another world, has not yet been achieved. But the path towards such a detection, which a generation ago seemed impossibly far away, is now visible. The tools exist, the methods have been demonstrated, the targets have been identified. What remains is the painstaking work of accumulating observations, building better models, and applying rigorous scientific standards to the interpretation of each new result. This work is underway, driven by Webb and the community of scientists who are using its data. The universe that Webb is revealing with its unexpectedly early galaxies, its potentially life-bearing ocean worlds, its magnetized ice giant with confirmed auroras and mysterious atmospheric heat patterns, is one that has been waiting to be seen. The physics that produced these phenomena was always there. The instruments to detect them are only now becoming available. What the next decade of Webb observations will reveal is genuinely unknown. But given the pace of discovery in the first few years, and given the observational programs that are planned and underway, the scientific picture of the universe will be substantially different in 2035 from what it is now. New records will be set for the most distant galaxy observed. New atmospheric detections will either strengthen or complicate the picture of potential biosignatures. New solar system observations will reveal more of what the outer planets have been hiding. Each discovery will generate more questions than it answers, because that is how science at the frontier operates. The questions Webb is generating today are better than the questions we had before Webb, more specific, more testable, more connected to real observable phenomena. That is progress, even when the answers are not yet known. The universe has been busy for 13.8 billion years. It formed its first stars while the plasma of the Big Bang was still cooling. It built its first galaxies while the rest of the universe was still mostly gas. It has been generating organic chemistry throughout that time, in the atmospheres of planets circling stars that formed billions of years before the Sunday. It has been producing auroras on distant ice giants since those planets formed from the early solar system's gas and dust. None of this waited for us to understand it. None of it paused while we developed the instruments to detect it. It was happening the entire time, in the dark, across distances and timescales that human intuition struggles to hold. Webb has given us a window into some of it. Not all of it, not even most of it, but enough to see that the universe's activity, its complexity, its potential for harboring the conditions of life are far greater than could be inferred from the instruments that preceded Webb. The silence that the universe seemed to be keeping was not silence, it was signal, waiting for a receiver precise enough to detect it. Webb is that receiver. And what it is hearing, in galaxy spectra and planetary atmospheres and auroral emission from ice giants, 45 astronomical units from the Sun, is the sound of a universe that has been doing extraordinary things for a very long time. The science is ongoing, the questions are sharper than ever. The instruments are the best humanity has ever built and pointed at the sky, and the discoveries are still coming. One aspect of Webb's scientific program that has not received as much public attention as the galaxy formation and biosignature results is its contribution to understanding stellar evolution, specifically the formation and early life of stars and planetary systems. Stars form from clouds of gas and dust in the interstellar medium. When a region of such a cloud becomes dense enough, gravity overcomes the pressure of the gas and the cloud begins to collapse. As it collapses, it heats up, and at the center, the temperature rises until nuclear fusion ignites hydrogen, burning to form helium, releasing the energy that powers the star. The surrounding material, instead of all falling onto the star, settles into a rotating disk of gas and dust called a protoplanetary disk, from which planets eventually form. The structure and chemistry of protoplanetary disks were poorly characterized before Webb because the disks are cold, dusty, and emit primarily in infrared wavelengths that ground-based telescopes struggle to observe due to interference from Earth's own thermal emission. Webb's sensitivity at mid-infrared wavelengths, from about 5 to 28 micrometers, is ideal for studying these disks. And its location in space, above Earth's absorbing and emitting atmosphere, allows it to detect the faint thermal emission from disk material that ground-based telescopes cannot. Observations of protoplanetary disks with Webb have revealed the presence of complex organic molecules, including water ice, carbon dioxide ice, and more complex carbon compounds in the cold outer regions of disks around young stars. These molecules are the raw material from which the building blocks of life might eventually be incorporated into forming planets. One of the most striking results from Webb's disk observations was the detection of water vapor in the inner region of a protoplanetary disk around a young star, a region where terrestrial planets might eventually form. Water is one of the most fundamental ingredients for life, as we understand it, and finding it in the zone where rocky planets form confirms that this material can be delivered to forming planets directly from the disk, not just from later bombardment by comets or asteroids. This connects to a long-standing question in planetary science. Where did Earth's water come from? Earth formed in the inner solar system, where temperatures during planet formation were high enough that water ice would not have been stable. Yet Earth has substantial water one might have expected it to be dry. The two most commonly proposed sources are comets, which are predominantly ice-rich bodies from the outer solar system, and carbonaceous asteroids, which contain hydrated minerals formed in the presence of water. Webb's observations of water in the inner protoplanetary disks of young stars suggest a third possibility, that water can be present in the inner disk from the start, incorporated into forming rocky planets directly. The chemical richness of protoplanetary disks observed by Webb extends beyond water. Sulfur dioxide, formic acid, and various carbon-bearing molecules have been detected in different disk environments. This chemical inventory is relevant to astrobiology because the organic chemistry of life on Earth, the chemistry of amino acids, nucleic acids, and other biological molecules is based primarily on carbon, hydrogen, oxygen, nitrogen, and sulfur. Finding these elements in the form of organic compounds in the environments where planets form suggests that the precursors of life's chemistry could be widespread throughout the galaxy, delivered to planets as they assemble from the material of their parent disks. This is not evidence that life arises wherever these compounds are present. The step from prebiotic chemistry to actual biology is not well understood and may require specific conditions that are not universal. But it does suggest that the molecular toolkit needed for life is not rare. It is produced in the environments where planets form and it is incorporated into those planets as they grow. Webb has also contributed to understanding the later stages of stellar evolution, specifically the deaths of stars. The same infrared sensitivity that allows Webb to see through dust to young stellar objects allows it to penetrate the dusty shells around evolved stars, stars that have exhausted their central fuel and are in the process of shedding their outer layers into the surrounding medium. Asymptotic giant branch stars, late-stage stars, in the process of losing mass through stellar winds and periodic pulses, surround themselves with complex dusty envelopes rich in carbon and oxygen compounds. These envelopes are the primary factories for interstellar dust and for complex molecular compounds that eventually become part of the interstellar medium. Understanding the detailed chemistry of these envelopes is important because their output determines the chemical composition of the next generation of protoplanetary disks and, ultimately, planets. Webb's observations of these evolved stellar envelopes have provided detailed chemical maps that show how different molecular species are distributed spatially within the outflowing gas and dust. This information constrains models of the nucleosynthesis, the production of heavier elements in stellar interiors, and of the molecular chemistry occurring as the stellar material mixes and cools in the envelope. These stellar evolution observations connect to the early galaxy results in a specific way. The galaxies found by Webb at very high redshifts were clearly forming stars rapidly. How rapidly those stars evolved through their life cycles and contributed to chemical enrichment of the surrounding gas depends on understanding stellar evolution. The better Webb's observations constrain stellar evolution models, the better those models can be used to understand the chemical history of early galaxies. The interstellar medium itself, the gas and dust between stars, has also been a target for Webb observations. The interstellar medium is not empty space. It is a complex mixture of gas in various states, from hot, ionized plasma near young massive stars to cold, dense molecular clouds, where new stars are forming, and dust particles ranging from small, polycyclic aromatic hydrocarbons to larger silicate and carbon grains. This mixture is the reservoir from which new stars and planets form and to which old stars return their processed material. Webb's infrared imaging of star-forming regions in the Milky Way and nearby galaxies has provided detailed maps of the interstellar medium at the sites of active star formation. The famous pillars of creation in the Eagle Nebula, photographed by Hubble in 1995 in an image that became iconic, were re-observed by Webb in 2022 and 2023, revealing previously invisible details of the cloud structure and the young stars forming within the pillars. The infrared images showed jets of material streaming from newly forming stars that were completely hidden in visible light images, demonstrating directly how young stars influence their surrounding gas and dust. These observations contribute to quantitative models of star formation efficiency, how much of the gas in a molecular cloud actually ends up in stars versus being dispersed by stellar feedback. This efficiency is one of the most important parameters in models of galaxy evolution because it determines how quickly a galaxy's gas supply is converted to stars over time. Better constraints on star formation efficiency at the level of individual star-forming regions improve the galaxy evolution models that are being tested against Webb's high redshift observations. The breadth of Webb's scientific program, from the very earliest galaxies to the forming planetary systems in our own galaxy, to solar system planets, to the detailed chemistry of nearby star-forming regions, reflects a telescope designed to address the most fundamental questions in astrophysics simultaneously. Different observing programs target different types of objects, and the data from each program informs and enriches the interpretation of the others. Understanding the chemical composition of protoplanetary disks helps interpret the atmospheric chemistry of exoplanets. Understanding early galaxy formation helps constrain the history of chemical enrichment across cosmic time. Understanding stellar evolution helps model the life cycle of the elements that make up planets and, potentially, life. This interconnectedness is not unique to Webb. It is a general feature of astrophysics as a discipline. The universe is a single physical system, and phenomena at very different scales and epochs are governed by the same physical laws and connected through the flow of matter and energy across cosmic time. A telescope that observes across a wide range of targets and wavelengths is naturally positioned to reveal these connections. What is unusual about Webb is the breadth and depth of its capabilities combined with the timing of its deployment. It arrived at a moment when multiple important scientific questions, early galaxy formation, exoplanet atmospheres, stellar evolution, solar system, characterization, were all approaching observational bottlenecks that required a new generation of instrument to break through. Webb's capabilities happened to address multiple bottlenecks simultaneously, which is why its early results span so many fields. This breadth creates a scientific environment where researchers in different fields are paying closer attention to each other's results than might otherwise be the case. Cosmologists studying early galaxies are noting the implications for chemical enrichment timelines that matter to astrobiologists. Planetary scientists studying exoplanet atmospheres are drawing on disk chemistry observations to understand the origins of the molecules they detect. Solar system scientists are comparing Webb's outer planet observations to models developed for exoplanet atmospheres. The cross-field connections generated by Webb's program are a kind of scientific bonus, not explicitly planned for any individual observing program, but emerging from the breadth of the data being generated. As Webb continues its observations through the remainder of the 2020s and potentially into the 1930s, these connections will deepen. The catalogue of high redshift galaxies will grow large enough to allow statistical analysis of how galaxy properties evolved across cosmic time. The catalogue of characterized exoplanet atmospheres will grow large enough to identify patterns, which types of planets, orbiting which types of stars, in which orbital configurations are more likely to show specific molecular signatures. The solar system observations will build into a systematic characterization of the outer planets and their environments that will inform the planning of future missions. The scientific legacy of Webb will ultimately be measured not just by individual dramatic discoveries, but by the cumulative improvement in understanding across all the fields it touches. The early galaxies, the potential biosignatures, the Neptune auroras, these are the early highlights. They signal what the instrument is capable of and point toward what is yet to come. The universe is vast, old, and complex. Webb is one instrument with one finite lifetime of observation. It cannot observe everything. What it can do, what it is doing, is systematically improve the quality of information available for the questions that matter most. And the questions that matter most, as revealed by its first years of operation, are the ones that concern the origin and distribution of complexity in the universe. How structures formed from simple beginnings, how chemistry evolved from primordial simplicity to the richness needed for biology, and whether that biology has emerged not just once on Earth, but more broadly across the cosmos. These questions may not be fully answered in Webb's operational lifetime, but they will be better answered, more constrained, more specific, more connected to real observable phenomena than they were before Webb began to look. That is the nature of the instrument and the nature of the science it is enabling. Not instant answers to ancient questions, but steady, systematic progress toward an understanding of the universe that is more accurate and more complete than what came before. The discoveries are real. The questions they raise are genuine, and the scientific work needed to answer those questions is underway, one spectrum at a time, one transit observation at a time, one deep field image at a time. The universe has been telling its story for 13.8 billion years. Webb is helping us read more of it than we have ever been able to read before. There is one more thread in this story that deserves careful attention: the role of dark matter in all of it. Dark matter is one of the most important and least understood components of the universe. It accounts for approximately 27% of the universe's total energy content, roughly 5 times more mass than all the ordinary matter made of protons, neutrons, and electrons combined. Dark matter does not emit, absorb, or reflect light at any wavelength. It cannot be directly observed with any telescope. Its existence is inferred entirely from its gravitational effects on ordinary matter. The evidence for dark matter is overwhelming and comes from multiple independent sources. The rotation curves of spiral galaxies, the measurement of how far stars orbit at different distances from the galactic center, cannot be explained by the gravity of the visible matter alone. Stars in the outer regions of galaxies move much faster than they should if only the visible stars and gas were exerting gravitational force. Something invisible must be providing additional gravitational pull throughout the disk and in a large halo surrounding the galaxy. Galaxy clusters, the largest gravitationally bound structures in the universe, contain far more mass than can be accounted for by their visible stars and gas. This additional mass is inferred from 3 independent methods: the velocities of individual galaxies within the cluster, the temperature of the hot gas that fills the cluster and radiates X-rays, and gravitational lensing, the bending of light from background galaxies by the cluster's gravitational field. All 3 methods agree that most of the cluster's mass is invisible. The cosmic microwave background fluctuations, measured by Planck, encode information about the relative amounts of ordinary matter and dark matter in the early universe, and the inferred amounts are consistent with the values derived from galaxy rotation curves and cluster masses. The Big Bang nucleosynthesis predictions for the abundances of light elements, hydrogen, helium, and lithium produced in the first few minutes after the Big Bang match observations, only if the total amount of ordinary matter is about 5% of the total energy content, consistent with the dark matter hypothesis. In standard structure formation theory, dark matter plays a central role. It was dark matter, not ordinary matter, that first began to clump under its own gravity in the early universe, forming the large-scale scaffolding called the cosmic web that ordinary matter later fell into. The filaments, walls, and voids of the large-scale structure of the universe reflect the distribution of dark matter halos inside which galaxies formed. The problem that Webb's early galaxy discoveries pose for this framework is specifically about timing. Standard models of dark matter structure formation, the lambda CDM model, predict how quickly dark matter halos of different masses should form at different epochs. The halos that would host galaxies like MOM Z14 should, in the standard model, have been relatively rare and relatively small at the epoch when this galaxy is observed. The very existence of MOM Z14 suggests either that dark matter halos formed more efficiently in the early universe than the model predicts, or that the baryonic matter, the ordinary gas converted into stars, more efficiently than current models assume. Both of these possibilities have been explored theoretically. Some models invoke a different form of dark matter, not the cold, collisionless particles assumed in the standard lambda CDM model, but warmer or more interacting particles that would have different clustering properties in the early universe. Warm dark matter particles, with masses and velocities that allow them to travel significant distances before clustering, would produce a different pattern of early structure formation than cold dark matter. In some scenarios, warm dark matter could actually produce more concentrated halos at early times in certain mass ranges, potentially accelerating early galaxy formation. Other approaches stay within the cold dark matter framework, but modify the modeling of how ordinary matter behaves within dark matter halos. The conversion of gas to stars is regulated by feedback processes. Supernovae blow gas out of forming galaxies, preventing all the gas from turning into stars at once. The radiation from massive stars heats surrounding gas, slowing its cooling and collapse. Black hole activity at galactic centers can drive powerful winds that clear gas from the central regions of galaxies. If these feedback processes were less efficient in the very early universe, perhaps because the first galaxies were too small for feedback to escape effectively, then star formation rates in early galaxies could have been much higher than current models predict, resulting in more massive and brighter galaxies at early times. The answer, when it comes, will likely involve some combination of these factors. Early galaxy formation is not a single process, but the outcome of many interacting physical processes, each with its own dependence on the conditions of the early universe. Disentangling these processes requires both better observations and better theoretical tools. Webb's role in this is to provide the observations. The theoretical and modeling work is being done by a large and active community of computational cosmologists who run large-scale simulations of galaxy formation in the context of different dark matter and feedback models. The goal is to identify a combination of model parameters that reproduces Webb's observations of early galaxies while remaining consistent with all the other constraints on the cosmological model. This is a constrained optimization problem with many parameters and many data points. The data from Webb are being integrated into this effort, pushing the theoretical community to develop models that can account for the observed abundance and properties of early galaxies, while also reproducing the well-established features of the cosmological model at lower redshifts. The outcome of this process will be a refined understanding of both dark matter's behavior in the early universe and the physical processes that govern galaxy formation. Whether that refinement requires minor adjustments to the existing framework or something more fundamental remains to be seen. The same dark matter that drives galaxy formation on cosmological scales also plays a role in the environments of individual galaxies relevant to the search for life. The dark matter halo of the Milky Way extends far beyond the visible disk of stars, providing the gravitational well that holds the galaxy together and influences the orbits of stars throughout the disk. The Sun's orbit in the Milky Way, which determines how Earth moves through the galactic environment over millions of years, is governed partly by the distribution of dark matter in the galaxy's halo. This matters for astrobiology in a subtle way. Earth's passage through different regions of the galaxy as it orbits the galactic center, sometimes closer to spiral arms with their elevated star formation rates and associated supernova activity, sometimes in quieter inter-arm regions, modulates the cosmic ray flux and the frequency of potentially disruptive nearby stellar explosions. Some researchers have proposed that the timing of mass extinctions on Earth correlates with the Sun's passage through regions of elevated astronomical activity, though this hypothesis remains speculative and contested. If dark matter is distributed differently than current models suggest, for instance, if it forms smaller, denser clumps than standard cold dark matter predicts, then the gravitational environment of the galaxy would be different from what is assumed, and the history of the Sun's galactic orbit would need to be reinterpreted. This is a small effect and not directly relevant to Webb's current observations, but it illustrates how the unsolved problems of dark matter physics connect, even indirectly, to questions about Earth's history and the conditions for life. The fact that so many different scientific questions converge on the same set of fundamental unknowns, what dark matter is, how the first galaxies formed, whether life exists elsewhere, is one of the things that makes this moment in astrophysics unusually interesting. Webb is generating data that is relevant to all of these questions, not because it was designed to answer all of them, but because the physical universe is structured in ways that make these questions deeply connected. The same early universe conditions that produced the first galaxies also set the conditions for chemical enrichment that eventually allowed rocky planets to form. The same atmospheric chemistry that might reveal biology on K2-18b also informs our understanding of how planetary atmospheres evolve over time. The same infrared capabilities that allow Webb to probe early galaxy spectra also allow it to characterize the dust and molecules in protoplanetary disks. The scientific program of the next decade will weave these threads together. Researchers in cosmology, planetary science, astrobiology, and stellar physics will be drawing on the same datasets, comparing notes, and building a more integrated picture of how the universe generates and sustains the complexity that makes life possible. Webb is the common thread running through all of it, the instrument precise enough to detect what was previously undetectable, sensitive enough to see what was previously invisible, and broad enough in its wavelength coverage to address multiple fundamental questions in a single observing campaign. What it is finding systematically and across multiple disciplines is that the universe is richer, more active, and more full of potential than the picture assembled before it began to look. Early galaxies more massive than predicted, ocean worlds with unexpected atmospheric chemistry, ice giants with previously undetected auroras and unexplained heat patterns, protoplanetary disks full of organic molecules. Each of these results is a data point in a larger pattern. The pattern is one of a universe that does not withhold its complexity until conditions are perfectly arranged. It builds complexity wherever the physics allows, faster than expected, in places and at times that were not predicted. Whether life is part of that complexity, whether biology is a general outcome of the universe's chemistry under the right conditions, or a rare accident that happened once on Earth, Webb cannot answer definitively. But it is providing the data that will eventually allow that question to be addressed empirically rather than philosophically. That is what has changed. Not just what we know, but what it is possible to know. The frontier has moved closer. The tools exist. The observations are accumulating. The universe has been building its complexity for 13.8 billion years. We have been trying to understand it for a few thousand years, with instruments precise enough to ask the hardest questions for only a few decades. Webb represents the current limit of what we can perceive. And what we can perceive, it is showing us, is extraordinary.